Hello and welcome to the lecture series on research in power electronics. And today in this lecture I would be talking about a variable structure nearest level control scheme that we have developed for multi-level inverters. I am Dr. Adil Sarwaf from the Department of Electrical Engineering, Aligarh Muslim University. So let's start with the basics of inverter. Inverter could be classified in multiple ways. An inverter could be a line commutated inverter or a force commutated inverter, or we can classify an inverter into a single phase or multi-phase inverter. And uh, in recent past we have since research is going on for more than three phases for more than three phases drive system. So we have more than three phases inverter system also coming up. Then we have a classification based on the conventional two level, in which we have the square wave and the quasi square wave, and the multi-level inverter. In multi-level inverter, the number of levels in the output voltage is more than 2, or rather more than more than 2, so 3 and above. Normally it's an odd number, 3, 5, 7 and 9 and so on. And similarly, multi-level inverter could again be classified as multi-source fed multi-level inverter or single source fed multi-level inverter. In multi-source fed multi-level inverter, the input supply is more than 1. While in single fed source multi-level inverter, we have got only one DC power supply, and rest of the levels that are generated in multi-level inverter are generated by the use of switched capacitor that are used in multi-level inverters. Charging and discharging those capacitors in a complete cycle is done in such a way that the voltage after one complete cycle remains same. So then something about the inverter application. We would be seeing inverters in grid application and in HVDC transmission system, in industrial application, and even in home appliances. Moving ahead, let's talk about the disadvantage or shortcomings of a conventional inverter. A conventional two-level inverter, as the waveform shown here, has got two levels, either plus V0 or minus V0, and the total harmonic distortion is quite high. It is around 47.03%, and the third harmonic or the fifth harmonic, and similarly seventh harmonic, they are quite high in the output voltage waveform. You could see here that in case of two-level inverter, it is more than 30%, the third level harmonic. Similarly, the fifth harmonic is around 20%, the seventh harmonic is around 15%. So this is much more than what is the restrictions that has been put in place by the IEEE 519 standard, which says that if the voltage level is less than 1 kilovolt, then the individual harmonics should be less than 5%, and the total harmonic distortion should be less than 8%. And for higher levels, then we have again more stringent conditions placed, like for voltages lying between 1 kilovolt to 69 kilovolt, we should have individual harmonics less than 3%, and the total harmonic distortion should be less than 5%. Similarly, for even higher levels, the conditions are more stringent. So the problems with this two-level inverter is that it has got higher harmonics, the higher voltage stress is there on the switches. So you could see that since voltage is switching between plus V0 and minus V0, that means this entire stress has to be bear by one or two switches that are present in the conventional two-level inverter. Say we have got a two-level inverter, an H bridge inverter, say, and and this is the load. So when it is conducting, say 1 and 2 are conducting and 3 and 4 are also there. Say for example 1 and 2 are conducting, so current will be moving in this fashion. Okay, so the stress that would be appearing across 3 and 4 would basically be the voltage, the stress across V3 and stress across V4. It will be equal to the input voltage, the VDC, or V0. If you since I am representing here it by V0, say let be V0. So this is quite high. This is quite high. Similarly, no boosting feature is available in case of two-level inverter. You know that we have to employ some control strategy to control the output voltage of the inverter, because most of the application requires some controlling mechanism in the output voltage. So no, we employ some modulation schemes. So modulation schemes are employed. So the problem with this modulation scheme is that if you are using sine PWM or you are using SV PWM technique, the output voltage is always less than the ratio between the RMS of the output voltage and the input DC voltage is normally less than 1. It is less than 1. So no boosting is available in case of two-level inverter. While in case of multi-level inverter, we have got switched, we have got staircase type of waveform, something like this, staircase type of waveform in the output voltage, which resembles closely a sinusoidal wave. Okay, the more number of levels, the more this waveform is close to a sinusoidal wave, isn't it? And the more the waveform closer to sinusoidal wave, the harmonic profile would be better. That means the THD would be lesser. So it has got better harmonic profile and similarly low dV by dt stress. Now you see the movement from one state to the other state. Say this entire voltage is V0 and it is 0 and this is minus V0. So if there are 1, 2 and 3 levels in the positive half, so that means this is V0 by 3, this is also V0 by 3 and this is also V0 by 3, isn't it? So the movement is from 0 to V by 3 and then from V by 3 to 2V by 3. So this is 2 by V and this is 3V by 3, which is V by 3, and this is V0. Okay, so that means the stress that will be appearing across the switch would be much less as the number of levels increases. So that is one of the advantage. Then higher inverter rating. Now, one interesting feature of multi-level inverters that especially say we are talking about CHB, you will see shortly, the cascade edge-bridge inverter has got a feature of modularity. So you can add number of similar units to the existing inverter and you can enhance the rating of the inverter. So very high level inverter rating can be obtained in such type of configuration. Then low filter requirement. The filter requirement would be definitely be quite less since the THD is less, so and the harmonic profile is very smooth, very having lesser harmonics, so the filter requirement is less. Then lower input current distortion, similarly the efficiency would be higher. Okay, that's fine. Let's move ahead. Now talking about some types of multi-level inverters. So the first being the diode clamp, then flying capacitor, then cascaded edge bridge multi-level inverters. They are quite popular, and I think they are in market since 2-3 decades. Uh, uh, okay. So we will be taking up one of the configuration, and we have taken cascaded edge bridge multi-level inverter for our study. And cascaded multi-level inverter, since it has got a modular structure, I told you this is the structure of CHB. So you can just add one unit of CHB into the existing configuration, and you can enhance the rating and consequently the number of levels also. There are two forms of CHB. One is called the symmetric configuration, and other one is asymmetric configuration. In symmetric configuration, these voltages V1, V2, the DC voltages, they are equal, while in asymmetric they are unequal. So in unsymmetric configuration, we can obtain a much higher number of levels compared to symmetric configuration, but definitely at the cost of having different sources of different voltage levels. Okay. So we have selected this topology for testing our modulation scheme that we have developed. And one more advantage that there is no need for any capacitor or diode in case of CHB. Okay, now coming to the switching table, in 7-level inverter and 9-level inverter, you need to follow these switching schemes in order to obtain these output voltage levels in the output voltage waveform. Similarly, 9 level, you have to follow this scheme. This is actually 1, 4, 6 are the switch numbers. Okay, fine. Similarly, for 11 level, we should have at least 3 bridges, 3 sets of uh, 3 sets of CHBs, 3 sets of H bridge rather. Okay, and 13 level can also be obtained with 3 sets of H bridge. But this is the switching sequence that need to be followed in order to generate these 13 levels in the output voltage waveform. Now, as I told you that there need to be some modulation strategy to control the output voltage. Moreover, this modulation strategy is also required to improve the harmonic profile. Okay, and that is what is the intention of our work, which I would be discussing shortly. Then I can classify the modulation strategy into two broad categories. One is the high frequency modulation scheme, in which the phase shifted PWM and level shifted PWM comes. Okay, phase shifted PWM is like you have these types of signals which are phase shifted from one another. Rather, it is okay. Let me show here. So this is phase shifted. So another carrier signal is phase shifted from the earlier one. For n levels, you need to have n minus 1 carriers. Okay. Similarly, for level shifted, the other level is here. Another level is here. So there is difference in the magnitude. Actually, start from this point. Sorry, something like this. Okay. So this is level shifted, and this is phase shifted PWM scheme. So these are basically the carrier waves which are compared with sine wave. There is sine wave, and it is compared with that, and consequently the switching sequence is obtained, and it is given to the various IGBTs of the multi-level inverter. Then the other one is the low frequency modulation scheme, in which we have got this selective harmonic elimination and selective harmonic mitigation and nearest level control scheme. Okay, and then let's come to the nearest level modulation strategy. It is quite a famous strategy, and it is a low frequency modulation strategy. So one of the advantage with low frequency modulation strategy is that the switching losses would be quite less. The switching losses would be less. Okay, why it would be less? Because since it is operating at a very low frequency level, so the switches are turned on and off normally at the fundamental frequency, or 2 or 3 times the fundamental frequency, so the switching losses are very less. So that's why it's preferred for high power application. Its implementation is quite simple, as I will show you after 1 or 2 slides. And the drawbacks of SHE can be eliminated. What are the drawbacks of SHE? SHE, I didn't talk about it in detail, but actually this SHE is selective harmonic elimination. And in harmonic elimination, we actually have multiple equations, and I would be hopefully doing one video on selective harmonic elimination also. I had already done it for 2-level inverters. You can watch it for 2-level, and selective harmonic elimination is it can be used for multi-level inverters also. The problem here is that you have got multiple equations, and those are transcendental equations and require complex mathematics to solve them, and to solve them uh, in real time is a big challenge. Okay, so normally what is done, solution is obtained before going for online implementation, and those solutions are actually stored in what we call in lookup table. Okay, so the angle values, say for 5-level inverters we have got 2 angles, alpha 1, alpha 2. Those values are stored corresponding to each modulation strategy, and those values are fetched from the microcontroller and can be given to the control scheme, and then controlling the output voltage is possible. But again, this real-time implementation is difficult in SHE, so that can be eliminated when we are using nearest level control. Now coming to nearest level control implementation, actually you see what happens in nearest level control. We have got a reference sine wave here. This is a reference sine wave, and it is compared with a constant voltage like 0.5, 1.5 and 2.5. These numbers are actually compared with this sine wave, and whenever this sine wave becomes greater than, say, 0.5 volt, then this there is a change in level. So earlier, say, it was at level 1, and when it changes to actually 0.5 should come here, 0.5 should come here, should be 1.5, should be 2.5, should be 3.5, and so on. So there was a slight mistake here. Anyway, so 0.5 is here. So whenever sine wave increases value above 0.5, then level changes from 0 to level 1. Similarly, when it changes value from more than 1.5, then the level shifts from 1 to 2, and it changes its value from more than 1, say 2.5, then the level shifts from 2 to 3, and similarly it moves from 2 to 3 to 4, and so on. So this is the concept of nearest level control. Okay, so the important term here is this 0.5 and 1.5 and 2.5, these numbers, which are basically used to compare with the varying sinusoidal wave. and this is sinusoidal wave m sine omega t. Okay, okay, or rather n times m sine omega t. Okay, n is number of positive levels only. Fine. Okay, so this will be 1.5. Okay, so this is how NLC is implemented. So let's move to now the scheme that we have proposed, which is the variable structure modulation scheme. In this scheme, we have not kept this constant DC level 0.5, 1.5 constant as such. Okay, they are taken to be variables like G 1 plus G and 2 plus G and so on. Okay, so if that is the case, now our intention is to find the value of this G such that the THD obtained is minimum for every value of modulation index M. Okay, I hope you understand what's the objective. The objective is not to keep these values 0.5, 1.5 and 2.5, rather keep them G 1 plus G and 2 plus G and find a relation between G and M, or rather find a function between G and M which relates value of G to M. For each value M, there should be a value of G such that the THD is minimum. Is it fine? So this is the concept of the variable structure nearest level control, and so this is the flow chart how it can be implemented in a microcontroller. Okay, so here you could see that I have shown here that total harmonic distortion. If I try to plot the total harmonic distortion for each value of G, and for each M, we have got this type of waveform. Okay, so these waveforms are for increasing values of M modulation index. So this is for highest value. I think this is for M equals to 1. Okay, so you could see here that for modulation index 1, the minimum value of THD, this is THD on the y-axis, is obtained for value somewhat at 0.4 and not 0.5. Okay, similarly for a value of M, say I think there is a difference of 0.01, so it will be 0.9, the next value, this value. So you could hear that there is a shift in the value, minimum values, and I have drawn this line for that, and this is basically the locus of the line for which the value of THD is minimum. Okay, so what is this line? This line is basically corresponding to for each M we try to obtain G where the THD is minimum, so that results in a line, a locus of line, and if I project it in GM plane, this is G on the x-axis and this is M. Now M will vary from 0.75 to 1 when we are talking about say I think for 9-level inverter. Okay, it will vary from 0.75 to 1. Why is it so? Because you see, so if this is your sine wave and say these are the levels. Okay, so if I reduce the modulation index, this is basically a m sine omega t. I told you that. So if I am reducing this m, then this is going to reduce. Okay, and then a point will come when it will not go above this. So number of levels will become less. Okay, so to obtain the maximum number of level, there is a limit on m also. So you cannot go beyond this value 0.75. And let me tell you that when you will apply nearest level variable structure nearest level control, this value also goes down. The beautiful thing about the variable structure nearest level control is that this value also gets down. Okay, so for NLC you will find that if you go beyond below the value of 0.87, that is m is less than 0.87 something value around this, then the levels reduces. While in case of variable structure nearest level modulation, you can go up to a value of 0.75. Okay, so that's the concept. Now why we have named it variable structure? Because for different levels we have got different structure of G, that is a different relation between G and M. They all will be straight lines as I had told you, but the relation between G and M are different at different levels. And even for say I'm working on line level and I have to work in the range this, when modulation index lies between 1 by 2 and 3 by 4, in that the structure of G will be different from what we have when I am working in the range when M is greater than 3 by 4. Okay, I told you that it is definitely going to come down the number of levels. Here the number of levels will be 9, here the number of levels will be 7, then here it will be 5, it will be 3 here. Okay, the similar thing will happen with the nearest level control also, but the good thing is that we have raised this limit when the number of levels reduces. Okay, so that's the idea. So I hope you understand. Now we have actually projected this line on this M and G plane, and we can obtain this straight line, and we can obtain the equation of the straight line which correlates this M and G. So you can obtain the expression of G as a function of M. So you put in all the values which lies in this range and you will get the value of THD to be minimum. And similarly you will find you can find out the value of the relation between G and M for 11 and 13 levels. Rather we have done it for N levels in our paper that appeared in IEEE Access. Okay. And another interesting thing is that even the third, fifth and seventh harmonic has come down. That level has come down in case of variable structure nearest level control screen. VSNLC or VSNLM, you can call it variable structure nearest control or variable structure nearest modulation. You can call it both. So the lower order harmonics in case of VSNLC is less than compared to NLC, the conventional nearest level control. Okay, and THD is, you could see here, that is for entire range of modulation index, the THD is less. Even for this region it is almost same, almost overlapping. But for all rest of the values of M, I'm changing M from this 0.5 to 0.6 for 0 until 1, and this is for 7 level CHB. For 9 level CHB also you could see that all the values of THD for M varying from 0.5 to 1, it is less. And interesting thing is that you see what is these bar graph, they tell these two, this and this, and this one is for VSNLC, NLM or whatever you call NLM, and this is for NLC. Okay, So at 0.56 and 1.8. Similarly, for different modulation index, you could see in most of the cases, although there are some exceptions here, it is greater. But in most of the cases, you will find that the third harmonic and the fifth and even the seventh is less in case of variable structure nearest modulation compared to the nearest level control scheme. Okay, and a similar trend is for 11 and 13 level. So we have done studies for 7, 9, 11 and 13, and we have concluded that variable structure nearest level control is a better option to go for low level modulation scheme compared to nearest level control, and even with selective harmonic elimination. We have done studies with selective harmonic elimination also. So in selective harmonic elimination, these are the angles that are obtained. Okay, I think we have used particle sum optimization to obtain these angles for 7 level and for 9 level. For 7 level, we will have 3 angles. Okay, so this is your 7 level voltage waveform. So 1, 2, 3, 4, 5, 6, 7 levels. So angles are, this is the first one, alpha 1, second is alpha 2, and the third one is alpha 3. Similarly, so this is 0, this is pi, and this will be pi minus alpha 1, pi minus alpha 2, pi minus alpha 3. Okay, and so this is pi minus alpha 3. Fine. So these are the angles that have been obtained using particle sum optimization. If you use any other scheme, it will be near about that. The interesting thing is that the THD that we obtained in case of the selective harmonic elimination and in case of the variable structure nearest control, then the variable structure nearest level modulation scheme scores better. In case of 7 level, in case of 9 level, in case of 11 level, in case of 13 level, in all the cases. Okay, so, and this is the circuit for the implementation of the scheme. We have tested it on hardware, and we have even found out that hardware results are also better. And definitely, if theoretical results are giving lesser value, so and it is mathematically obtained, so hardware results are bound to give the same type of results. So you could see here that for NLC, and this is for 7 level, you could see that 0.5 and G 0.5, the THD is 16.5%, while in 0.9 the same values, but G is different. For same modulation index, I have used VSNLM. G is different and THD is 12%. So drastic reduction. Similarly, for 9 level also the THD 12.5%, here 9%. In case of 11 level also the THD is here it is 9.4%. It has reduced to 7.3%. Here for 13 level it is 6.7%, reduced to 6.5%. This work appears in implementation of novel variable structure nearest modulation scheme in Cascade Edge multi-level inverter that appeared in IEEE Axis. Okay, so I hope this is a better scheme to be used in modulation scheme in a multi-level inverter, and so that's all. Thank you for watching.